introduce Professor Kotaro Kawai from Gakushuin University. Yes, he's before joining that famous private university, he was at Tokyo University, and he told me that Gakushuin is very small but had very strong tradition in geometry, topology, and Kotaro spent his time after retirement here, right? Okay, so today Kotaro Kawai give a talk on deformed Donaldson connection. So please.
Yes, thank you for introduction. First of all, I would like to thank the organizers for giving me an opportunity to speak in this seminar. Yeah, it's very great to speak here. So, today I will talk about deformed Donaldson-Thomas connections. And so this is some kind of a connection defined on a line boundary over the D2 manifold. So I first recall some background, say about what is Z2 or some related topics, and then I'll explain about the deformed Donaldson-Thomas connections. Okay, so let's review the holonomy groups. So yes, maybe many people will know the definition of a holonomy group, but it doesn't matter whether you know the definition or not. So say the holonomy group is one of tools to study the structure of the Riemannian manifold, MG. So if we have the Riemannian manifold, then we can define some Lie group, holonomy group, hol G, and this is one of the tools to study the structure of the Riemannian manifold. But there are many possible choices of holonomy groups, but the possible holonomy group is classified under some canonical assumptions. So this is a classical theorem by Belgier in 1955, and these four lines explain what is canonical assumptions. So let MZ be a simply connected Riemannian manifold, and which is irreducible. Now, irreducible means that Riemannian manifold is not a product of Riemann manifolds and even locally, and it is not a locally symmetric space. This means that the Riemannian curvature R is not parallel. So then the possible holonomy group is one of the following. So SN and UN, SCN, SPN, SP1, SPN, and Z2 and spin 7. So SON case is the most generic, and this corresponds to that. This manifold is orientable, and the UN case is the manifold is a Kähler, very famous case, and SUN case corresponds to the Calabi-Yau case, and there are some cases. And now today's main topic is about the D2 case. So and these two guides, D2 and spin 7, are called exceptional holonomy groups. But today I will focus on the D2 case. Okay. So next, so G2 is some exceptional Lie group. So I'll explain what is Z2 very quickly. Okay, you know. So and Z2 can be defined as the automorphism group of the octanion. So which means automorphism means that each element of Z2 preserves the multiplication of octanion. So there's a canonical multiplication on the octanion, and Z2 preserves its multiplication. So this is the definition of Z2, but maybe, as you know, the multiplication of octania is very complicated. It is not even associative. So, but to make things simpler, we consider the following. So first, identify all octanion. This is I know O with R plus imaginary O. So R is the real part, and imaginary O is imaginary part. And R, so as a vector space, this is R plus and R7. So the strategy is to describe the multiplication of the octanion by the 3 form on R7 space. So, so 3 form on the imaginary O. So by this formula. So that is multiplication is an operation and that generates a vector from 2 vectors. So if we have 2 vectors and then take an interior product, then we have a 1 form. But take the metric dual, then we also obtain a vector L in R7, imaginary part of O. And now here we assume that U and V are mutually orthogonal. So in this sense, multiplication of O is described by the 3 form phi 0. And so D2 is an element of automorphism. So D2 is the automorphism group of octanion. So we can describe D2 in this way. So D2 is an element of ZL7R that preserves this 3 form phi 0. And in fact, we know that this is a subgroup of SO7. And this is non-trivial fact, but anyway, it is true. So this is a definition of the Lie group Z2. And now the next one comes from the general theory for holonomy groups, say so-called holonomy principle. So if the holonomy group is contained in this Lie group Z2, then we can construct a parallel 3 form phi, by some using parallel transport. But anyway, this phi is not unique, but in this talk, fixing such a phi, and we call X7 phi Z2 manifold. Here we always assume that manifold is 7-dimensional, and so we call this triple called Z2 manifold. So very roughly speaking, so D2 geometry is characterized by a 3 form phi. This 3 form phi plays a very important role, just as in the Kähler geometry, Kähler 2 form plays an important role. So in this sense, D2 geometry is characterized by the 3 form phi.
Kotaro,
yes.
Let me say something. Yes, I think that's once you fix the group, even G2, then there exists only unique Varphy satisfies that stabilizer of Varphy equal G2, right?
In the case of holonomy is equal to Z2, so
because that's in linear algebra. So that is there nothing holonomy. You consider group as how many forms there is in my paper on the classification, at least that's on pink. I mean that's any 3 form. I cannot because there unique. That means that's a 3 form. For any not necessary that's associative, but given group, I mean that's the theory in algebraic invariant theory. Stabilizer is a unique invariant defined the Varphy. Yes, exactly. That's why that defines the form. Actually you can how to say that's you can that I noticed because I look at the paper 3 real form in R8 And if you see, that's a stabilized algebra Unix, but that's not yes, once the stabilizer defines and the group define, because the only stabilized algebra for each form, yeah. So that's a Djokovic. If maybe I misunderstood something, but we could discuss later, right?
Sorry, internet connection is very bad, so I don't understand what you said. So
I say that it taught me that you taught on the zero exit but uniqueness. My point is the following. That's a problem is not on manifold. Problem is a linear algebra.
yeah.
So given ask how many form have the given group a stabilizer. So the question, that's a stabilizer define the form uniquely. That's a linear algebra.
Maybe. But,
so for example, yeah.
But just this only this condition. But we have a freedom for the dilation, for example.
Yes. So that because we consider that SL a Varfi dilation. So dilation. So dilation, then it thank you. Yes. The only SCL classification, then yes.
Okay, so let's go further. So maybe from here, maybe some people find it this geometry is very, say, exceptional or something doing something special. But D2 geometry is very important because this geometry is related to many other fields. So the most related one is the Calabi threefold. So in some sense, and D2 manifolds can be considered to be the analog of a Calabi threefolds, because this is just because Lie group SU3 is contained in Z2. So for example, so if we have a Calabi 3 manifold, 6 means a real dimension. So if we have Y6, then S1 times Y6 is in fact a Z2 manifold. So then, in fact, there are many other similarities, but I will explain them later. So another way to consider this manifold is in the relation to 3 and 4 dimensional manifold. So maybe for these manifolds, can we consider higher dimensional analogues for the theory for 3 and 4 dimensional manifolds? So, for example, there's a Chern-Simon theory on 3 manifolds, which considers flat connections, and on 4 manifolds there is a Donaldson theory, which considers ASD connections. And nowadays, there were some people consider it's the higher dimensional analogues of these two guys, so flat connections and ASD connections. And now today, so their generalization is considered as their generalization for Z2 geometry is called Z2 instanton. And so so deformed Donaldson-Thomas connections, a topic in my talk, is also related to this Z2 instantons. So I will also explain this later. So, but anyway, so Z2 geometry is a very fascinating topic, at least for me. So okay, so let's go to the next slide. So another important wise notion is the calibrated geometry. This is introduced by Harvey and Lawson in 1982. So this calibrated geometry is also plays a very important role in Z2 geometry. So let's give some notions and give some examples. Okay, let's check it. First, we can define a calibration, and this is a closed differential form. So K form on n manifold on a Riemannian manifold and satisfying a certain condition. So I do not explain this condition, but from this calibration, we can define and calibrate the submanifolds. So this is a special class of a minimal submanifold, and this has very striking property. That is, every compact calibrated submanifold is homologically volume minimizing. This means it is volume minimizing in its homology class, and the volume is given topologically. Topologically, I mean the volume is given by the pairing of some homology class and a cohomology class. Yes. So if we have a calibration, this is some special closed differential form, then we can define special class of minimal submanifolds and call the calibrated submanifolds. So I do not give some detailed definitions of these, but I will give some examples. So for example, if a holonomy group is contain a unitary group, then the manifold is real 2n dimensional, and it is called scalar. So on a scalar manifold, there is a scalar form, and the scalar form is in fact a calibration. And in fact, the power of scalar form multiplied by some constant is also a calibration, and the corresponding calibrated submanifolds are called, in fact, complex submanifolds. Yes. So, and in the SUN case, this manifold is called the Calabi-Yamamoto manifold, and on Calabi-Yamamoto manifold there is a holomorphic volume form. And using the real part of that, we can define the calibrated submanifold, and it is called special Lagrangian submanifolds. And on a Z2 manifold, so we have, in fact, we can define associative or co-associative submanifolds. So in other words, these submanifolds can be considered to a generalization of complex submanifolds. So and I changed the color because this red guys and blue guys behave differently. So in the sense of deformation theories. So in fact, red guys have obstructed deformations in general, and blue guys have unobstructed deformations always. So this is very nice, very important properties. And this will be turned out to be useful in later. So now we introduce the calibrated submanifolds, and in fact, when we want to understand an original manifold via calibrated submanifolds, that's why calibrated submanifolds are considered to be very important. And so I will give some examples for this. So for example, a Gromov with the invariant. This counts as pseudo holomorphic curves in a symplectic manifold, and in fact, and this gives a very non-trivial invariant for symplectic manifolds. So using this submanifolds, so pseudo holomorphic curves, we can understand symplectic submanifolds. And previously I said, so this red guy, so complex submanifolds behave like associative submanifolds. So it may be a natural question that can we count associative submanifolds like counting of pseudo holomorphic curves? So this is so there are another kind of problems for counting. So for example, a Casson invariant for 3 manifolds counts flat connections, or a Donaldson invariant counts ASD connections on 4 manifolds. So and since D2 instantons are generalizations of these guys, flat connection and ASD connection. So it is natural to ask, can we count Z2 instantons? So this is very, so in this sense, calibrated submanifolds considered to be very important in Z2 geometry. So, and another important thing is a mirror symmetry. So I'll explain what is mirror symmetry in the next slide. But it was first considered for Calabia's threefolds. So this some very mysterious relations, and so but as I said, and Calabia's threefolds are very similar to Z2 manifolds. So it is natural to consider the mirror symmetry for Z2 manifolds. So from this, in fact, from this perspective, we can define deformed Donaldson-Thomas connections, the titles of today's talk. Okay, so in the next slide, I'll explain the mirror symmetry for Calabia's threefolds, and I'll explain how it is generalized to Z2 geometry. So, okay, so this is a very rough idea for mirror symmetry. Yes, mirror symmetry first appeared in physics, and it states that the two Calabian threefolds are related in very mysterious way. So, it was first appeared in physics, but in 1996, this Strominger, Yao, and Zastrow gives a mathematical conjecture of mirror symmetry. So very roughly speaking, mirror symmetry of Calabian threefolds will be explained in terms of special Lagrangian and dual torus, three-dimensional torus fibrations, including singular fibers. That is, if X6 and X6 star are mirror in some sense each other, then there should be some three manifolds B3, and there exists a fibration. There are fibrations F and F star, and each including singular fibers. And smooth fibers are dual special Lagrangian three torus, a dual in some sense. So the mirror symmetry is explained in terms of special Lagrangian fibration. So okay, so this is called SYZ conjecture now, and so considering this special Lagrangian fibration is very important in the study of mirror symmetry, and using this special Lagrangian torus fibration, and Liang and Yao and Zastrow consider the mirror of special Lagrangian submanifolds, calibrated submanifolds for Calabian manifolds. And in fact, special Lagrangian submanifolds corresponds to so-called deformed Hermitian-Yang-Mills connections, DHRIM connections, so, and via the real Fourier Mukai transform. So, and recently, DHRIM is considered very intensively, maybe by Professor Yao. So recently, DHRIM connections are very studied very well. So now I want to explain there is an analogous story for Z2 manifolds. Okay, so these are the story for Z2 manifolds. So now we have two Z2 manifolds, X7 and X7 star, and now we can replace special Lagrangian with co-associative. And because, as I said, special Lagrangian and co-associative behave similarly, so we replace special Lagrangian with co-associative. So we have if we have two manifolds, then there exists some three manifold B3, and there is a fibration, and smooth fibers are dual T4 or K3 surfaces. Yes, in the previous case, only torus appeared, but in this case, the K3 cast surfaces also appears. So this is a difference from the Calabi-Yau case. So in today's talk, I will focus on this T4 case, but T3 surfaces can be considered to be very important because in fact, Donaldson studies this the adiabatic limit of K3 relations. Here, adiabatic limit means the limit that takes the volume of 5 as it goes to 0. So this recently Donaldson studies this theory, adiabatic theory of K3 relations, and Yan Li also studies this type of theory. Yan Li was a student of Donaldson. Okay, so maybe the K3 relation should be very important, but now we want to focus on T4 case. But for T4 case, Li and Liang do a similar thing to the Liang and Yao and Zaslow. So Li and Liang do a similar thing for in Z2 setting. So if given a co-associative dual torus relation, then we can consider the mirror of associative submanifolds, and the associative submanifolds corresponding to deformed Donaldson-Thomas connections via the real Fourier-Mukai transform by the same method. So this is a top. This connection. So here, deformed Donaldson-Thomas connection appears in this context. Okay. So now I'll give a very detailed definition of deformed Donaldson-Thomas connections. So that is, first we have a Z2 manifold, and then suppose there is a smooth complex Hermitian line bundle. H is a Hermitian metric. And then a Hermitian connection nabla of LH is called a deformed Donaldson-Thomas connection, a DDT for short, or someone prefers to call this a deformed D2 instanton if this equation is satisfied. Yeah, here if nabla is a curvature of nabla, and we consider this guy is a pure imaginary number valued 2 form. Okay, so this is a very definition of the DDT connections. Okay, so but anyway, so okay.
Sorry, what are the non-deformed ones?
So sorry.
The ones that aren't deformed. What is the equation?
What the equation?
Well, you have the deformed Donaldson-Thomas connections. What is the equation for the? Oh, okay.
Oh, this one. I explain the relations. Okay. So yeah, okay. So as the name indicates, the DDT connection can also be considered as an analog of the Z2 instanton, because Z2 instanton is also called a Donaldson-Thomas connection. So and this can be defined by if nabla with star phi is 0, so the only second term appears. So there are some similarity between these two equations, and we expect that DDT connections will have similar properties to associative submanifolds and Z2 instantons, because DDT is a mirror of associative, and it is similar to Z2 instantons. Okay. So obviously, a flat connection is a DDT connection. This is a very definition of the flat connection and DDT connections. And I will give another example. That is a DHYM connection is in fact a DHYM connection in the following sense. So I'll explain what it. So if we have a Calabi-Yau manifold, omega is a Kähler form, metric, complex structure, and omega is a holomorphic volume form. And we consider the smooth complex Hermitian line bundle over Y. And as I said, X7 is 1 times Y6 admits a Z2 structure phi. And these which is given by this formula. And here, x is a coordinate for S1. Yeah, so and we can define phi, and it's hot 0. It can be defined in this way. And let phi be in a projection. So in this title, I said DHYM is DDT. This is DHYM is DDT in the following sense. So if we have a DHYM connection nabla of LH, then its product is a DDT connection of this product line bundle. So here, and the DHYM connection is defined by this formula. So the 0-2 part of the curvature vanishes, and imaginary part of this guy also vanishes. So this is a definition of DHYM connections. But we can prove this statement very easily because of these simple computations. So since star phi is given by this formula, omega squared by 2 minus dx wedge imaginary omega. So from this expression of star phi, we see that the left-hand side is given by the right-hand side. And in fact, this part can be described as an imaginary part of omega plus f nabla cubed, because omega is a real form and f nabla is a pure imaginary number valued 2 forms. So maybe you can easily see that imaginary part of this is equal to f nabla cubed plus 3 times f nabla wedge omega squared. So now, if nabla is a DHYM connection, the 0-2 part vanishes. So this part second term should vanish. And then, and further, if this guy is 0, then this one, f nabla cubed plus 3 f nabla wedge omega squared should vanish. So the first term also should vanish. But anyway, so this left-hand side should vanish. That is, then it implies that it is a DDT connection. Yeah, so this is a very consequence of a very simple computation. But in fact, what is interesting is we can prove the converse if Y is compact. But anyway, I'll explain this later. Okay, so this is a okay. So I'll give some. I summarize what I said here. So we have DDT. This is a mirror of associative, and it is analog of D2 instantons. And DHYM is in fact DDT in the sense of the previous slide, and the DHYM in fact a mirror of special Lagrangians. And special Lagrangians, in fact, associative submanifolds in the sense of, let's say, in the similar sense to the previous slide. And so we have this type of picture. And for associative submanifolds, we might consider the analog of Gromov-Witte invariants. And for D2 instantons, we might consider higher dimensional gauge theory. So we might count associative or D2 instantons to define some invariants of D2 manifolds. So it is quite natural. Maybe we might count DDT connections to define some invariants of D2 manifolds. It should be a very exciting problem. But what is it? The problem is that almost nothing is known about DDT connections until our work appears. So, for example, how about the deformation theory or modular theory, or do DDT connections indeed have similar properties of associative and D2 instantons? Yes. So mirror or analog with some kind of a conjecture. So we have to check this we have to check this rigorously, whether they have similar properties. So recently we consider the moduli theory and check if they have similar properties. So these are our recent work, and so the second one explains our future plans. So we hope to understand associative and D2 instanton by developing a theory of DDT connections. But it should be very interesting. Okay, these are our motivation for the study of DDT connections. Okay, so to study the analogy, we have to recall the properties of associative submanifolds. So, and these are main properties of the associative submanifolds, and we have 1, 2, 3, 4, 5 properties of the associative submanifolds. So the first one is about moduli space. So the moduli space of associative submanifolds is in fact a zero-dimensional and orientable if we perturb the D2 structure. So behave nicely under the perturbation of the D2 structure. And there is in fact an associated equality. This is a very fundamental algebraic identity, but there are many applications of this equality. For example, from this equality, we see that the D2 structure is a calibration, and we can characterize associative submanifolds by the vanishing of an some tensor, and which is very useful in deformation theory. And the third one is the properties of calibrated submanifolds, because it is homologically volume minimizing, and the volume is given topologically. The fourth one is related to the special Lagrangian. So if X is given by S1 times Calabi-Yau, this is the X7 is a D2 manifold, and every associative submanifold in X7 representing this homology class coming from Y6 is of the form point times L with L special Lagrangian submanifold. So if we fix a homology class in Y, then every associative is a special Lagrangian submanifold, in fact. So another property of associative submanifold is that they can describe that critical point of the Chern-Simons type functional. So these are some maybe main properties of associative submanifolds. And in fact, the D2 instantons have similar properties to the above. And so we have associative have these properties, and we could indeed show that similar properties to the above also hold for DDT connections. This is our main result. But the last one about the variational viewpoint was already by Carl-Giannis and Young. But so we have these we have shown the mirror version of these four facts, for properties. Okay.
So that you mean that but you don't have the compactness, right? Moduli space, orientable, and you perturb in the class of holonomy, or each class you perturb, which kind of perturbation?
So about this?
Yes, about the G2 structure inside the holonomy or inside the larger class.
I only assume that the G2 manifold, so it's contained in G2.
So that means you take a very large perturbation.
The first one.
Many people go.
The first one.
Yes, the first one, because the many people go perturbation to remain in the close or co-close form or close and co-close. That means holonomy. I mean, that's a perturbation is a very.
I mean, in the space of closed, we with the same cohomology class, in the same cohomology class for form. Yeah. Deformation
that
theory.
means that you don't know. You don't require just the perturbed structure also holonomy, or you require the perturbed structure is I mean just you know just holonomy that means constant, yeah, parallel G2 structure.
No.
And the user.
Because in fact, and deformation theory works for co-closed G2 manifold with co-closed G2 structure. So we do not assume holonomy restriction, and we only consider in the co-closed G2 world.
Yes.
Okay, so,
I see. Okay, thank you.
Okay. But now I do not explain the deformation theory in detail today. But I explained the deformation theory very roughly. So first, we decided the expected dimension of the moduli space, and it is in fact B1, the first batch number of the base manifold X. And as I said, and the moduli space is a smooth manifold if we part of phi in the space of co-closed G2 structures. And in fact, the third one is about the orientability. In fact, it admits a canonical orientation if all deformations are unobstructed. This condition only to assume that the moduli space is a manifold. Yes, orientability only makes sense for the smooth manifold. Yes, but we know that this orientability is a global property, so it is a little bit difficult property to consider. But we show these properties, but more precisely, and for each DDT connection nebula, and we can introduce the complex sharp nebula, and which is in fact a subcomplex of an elliptic complex. And the deformation of DDT connections is in fact controlled by this complex, as common with other deformation theories. Okay, so but that's a very rough idea of deformation theory. So we can see the similarity about the moduli theory, but now I'll explain the mirror statement of associated equality. So to explain the associated equality, we first need to introduce the notion of mirror with volume functional. Okay, so let's explain about it. So mirror with volume functional. I see there I found some comment. So I'll answer chat later after my talk, sorry. So anyway, I'll explain the volume of for connections. So now I give a setting. So X is a compact connected D2 manifold, and L is a smooth complex Hermitian line bundle, and A0 is a space of Hermitian connections of LH. And for connections, and we can in fact define the volume functional given by this formula. So volume is given by the integration of X of small v nebula. Here vol is a volume form introduced by the metric Z. And then small v nebula is given by this formula. So 1 plus f nebula cubed and da, 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 da. Yes, this is a definition of volume for connections. And in fact, the first one is the reason why we call this volume functional, because V is a mirror of the standard volume functional for submanifolds via the real Fourier-Mukai transform. So via the real Fourier-Mukai transform, we can construct this functional from the standard volume functional for submanifolds. And this functional is maybe famous in physics, and this V is called Dirac-Born-Infeld action in physics, DBI action. Maybe action in physics means functional in math, so DBI functional. So using this functional, maybe we can show the mirror of the associated equality. Yeah, this theorem is this is my most favorite theorem. So I'll explain, I'll write down it very explicitly here. So that is, for any Hermitian connection nabla, we have this type of algebraic identity. So some guys squared plus the defining equation with DDT connection squared plus and some guys squared and is equal to V nabla squared. And from this lead identity, we can see this characterization of DDT connection. And that is, for any Hermitian connection nabla, we have this inequality, and the equality holds if and only if nabla is a DDT connection. Maybe you can check this statement from this lead identity. Maybe I can show this here. So this equality holds. So if this is equal, then the first term and right-hand side are equal. So the second and third term should vanish. And the vanishing of the second term implies that nabla is a DDT. So we see. So nabla is a DDT. And conversely, if nabla is a DDT, then the second term should vanish. But in fact, we have this algebraic identity. So that is, if second term vanishes, the third term should vanish. So we see that this one and this and right-hand side are equal. So it means that the equality holds here. Yeah, very simple consequence. So, and we call this identity the mirror of associated equality because this can be obtained by the real Fourier transform. So this, in other words, this identity is predicted by a real Fourier transform. So this, and I showed this identity by some point-wise computation, but the computation was really tricky and complicated. So we would not have found this without the prediction by the real Fourier transform. But so this itself is very interesting identity, but this has very nice corollary, and that is for any DDT connection nabla, nabla is in fact a global minimizer of the volume, and the volume is given in fact topologically. So maybe this you can see. Maybe you can see the statement by the integration of this of the inequality. So maybe, but now you can see there's some absolute values, but it doesn't so much. So if nabla is a DDT connection, then V nabla as a large V nabla is given by the integration of this guy, the absolute value of this guy. So 1 plus 1 by 2 F nabla squared and star phi and volume Z. And this is in fact can be described using volume and first chunk class. So in this case, nabla is a global minimizer of V, and V nabla is given topologically. So this is very useful and very interesting corollary. So this is very useful, and we now explain another corollary of the theorem. So that is the statement says that on a flat line bundle, any DDT connection is in fact a flat connection. Yeah, so we in particular, the modular space of DDT connections is equal to the modular space of flat connections, and in fact it is a torus H1XR divided by H1XZ. This we can also prove this corollary very simply. So I'll explain here. So if we have a flat connection nabla 0, this is an obviously a DDT connection, and nabla be any other DDT connections. So as I said, for DDT connections, the volume is given topologically. That means B nabla and B nabla equals to B nabla 0. But the very definition of B nabla, this is an integration of this guy. But since nabla 0 is a flat connection, so F nabla 0 is equal to 0. So this B nabla 0 is equal to the integration X volume Z. So comparing these two guys, maybe you immediately see that F nabla should vanish. Yes, so in this sense, we see from the previous identity, yes, so any DDT, we see that any DDT is a flat connections. Yeah. Okay. So and the next self theorem says about gives another application. This characterizes the DDT connections on the product line boundary in terms of the moduli of DH-rhyme connections. So that is, so as I said, if we have a Calabi-Yau and the Hermitian line boundary over Y, and the product of the DH-Ym over LH is DDT. This is just as I said, and denoted by pi the projection. And then, in fact, using the mirror of associated equalities, and in fact, we also slightly use a mirror of special Lagrangian equality, and then the converse also holds. So by this first line, maybe it is very easy to see that the existence of the DH-Rym connection of L implies the existence of the DDT connection of the product line bundle. But in fact, we can also prove the converse. That is, the existence of the DDT connection of the product line bundle, then there exists a DH-Rym connection of L. And the second statement says that any DDT connection nabla tilde is essentially a DH-Rym connection. That is, for any DDT connection nabla tilde of pi L, and there exists a DH-Rym connection nabla of L, and a pure imaginary number value closed one form, and such that nabla tilde is equal to this. Yes, because by under the addition of closed one forms, the curvature does not change. So Guzai must appear here, but modulo closed one forms and the DDT connections are in fact the DH-Rym connections. Using this statement too, we can determine the structure of the moduli space. So if we denote MZ2 the moduli space of DDT connections, and MDH-Rym the moduli space of DH-Rym connections, then we see that this moduli space of DDT connections has a structure of direct product S1 times MDH-Rym. Yes, so we can determine the global structure of MZ2 in terms of MDH-Rym. So this is a very nice property. So, okay, so I only have 5 minutes, so maybe I can skip here. So, but in this slide, I want to explain that DDT connections are critical points of the Chern-Simons type functional. But this fact is not so important. Maybe I can skip this slide. The talk is left only 5 minutes. So now I'll go to next slide, and I give a summary of my talk. So in this talk, I introduce the DDT connection, and this is a mirror of the associative submanifold, and it is an analog of Z2 instantons. And DDT contains a DHYM connection, and DHYM is a mirror of special Lagrangian submanifolds. And for associative submanifolds, we can consider analog of Gromov-Witten invariants, and for Z2 instantons, we can consider higher dimensional gauge theory. And from these similarities, we can have the very canonical, natural questions. So can we count DDT connections to define invariants? And in the future, we want to understand the associative and D2 instanton by developing a theory of DDT connections. This should be exciting. And this is next one states that DDT connections indeed have the following common properties with associative and D2 instantons. So moduli is B1 and B1 dimensional and orientable, and if we part of this structure in the space of co-closed these structures, and there exists a mirror of associated equality, and this equality is very powerful. So, and using this equality, we see that any DDT is a global minimizer of V, and it is given topologically. And if X7 is a direct product of S1 and Calabi-Yau, and then any DDT is essentially a DHYM connection, modulo 1 forms. And sorry, this point, I do not explain this point, but DDT can be described as critical points of the Chern-Simons type functional. But this was proved by Carly, Yanis, and Liang. Sorry. So I also proved these properties for so the DDT connections, but in fact, we could also prove a similar statement in the spin 7 case, but except for the last ones. So in fact, what I said in this talk is also holds for spin 7 manifolds. This should be very interesting. So in the last slide, I want to explain the future work. So and recently we showed that there are many similarities between DDT connections and associative or Z2 instanton. So the maybe canonical question is, can we find more analogies, maybe by the real Fourier guide transform? Maybe this should be done more. So, and the next one is about the mirror with the say mean curvature flow. So we introduced the mirror of the volume functional, so it is very natural to introduce the mirror with mean curvature flow, but as it's the negative gradient of the mirror of the volume functional. Indeed, we can define the mean curvature as a negative gradient of vector field of V. And in fact, we could show the short time existence of this flow, mirror mean curvature flow very recently. But maybe, as you know, there are many results for mean curvature flow for submanifolds. So we expect that we may prove various results corresponding to the mean curvature flow for submanifolds. And next one is about a construction of examples. So as I said, DDT connection, flat connection and DHYM connection are examples of DDT connections, but there is a few examples known. Recently, examples are considered by Lotte and Oliveira, but their example are given on say manifold with a co-closed structure. So there are no known example on that on the D2 manifold, a manifold with torsion-free structure. But as I said, there is an obstruction that is for on a flat line bundle, every over a D2 manifold, every DDT is a flat connection. So we have to pick up some and non-flat line bundles. So the problem seems difficult. But the next one is about singular DDT connections. So to maybe if we want to define some enumerative invariants, we have to consider singular guides. But I have no questions about this. But maybe a compactness theorem for DDT connections might hold. For example, because for associative case or D2 instanton case are also already studied by these people. So these cases might be helpful for the compactness theorem for DDT connections. Okay, I'll stop here. Thank you for enjoying.
Oh, yeah. Yes, thank you. Yes. So you can also make the reaction. Yes. That's a very impressive. Yes, but I only see that Professor Akabulut has some question. Can you repeat here?
Yeah. Yes, just this will call mirror duality, attempting to course. Sorry, I check.
Akabulut. But
yes, I'm here. Yeah. Thank you for interesting talk.
Thank you for
there's a problem with your audio. I cannot hear you very well, but I heard the talk itself. So, but more or less,
I hear very well. I hear
Okay.
the Kotaro talk very well. Yes.
Maybe it is from my end. I don't know. So, I mean, it's a very interesting talk. I thought about these things 15 years ago with Salur. We were attempting to define a mirror duality, some kind of mirror duality inside of G2, seeing relating associative to co-associatives as some kind of mirror dual. I just was asking whether speaker knew about these papers. As well.
Sorry, in your paper, in your paper, sorry, I am reading your paper now. So to mirror dual. So can I? Could you tell me what you did in your paper?
I'm a little bit rusty. I don't know if I can remember the details, but the idea was every orientable, close orientable spin 7 manifold, it means 2 frame field, old theorem of Emil Thomas. And then you take this 2 frame field, cross product it, you get a associative 3 plane field, and take the dual of the 3 plane field, you get a 4 plane field. So this is a E plus V decomposition of G2 manifold. So a G2 tangent bundle of G2 manifold splits as 3 plane field and the 4 plane fields. And we were taking like vector fields in each, in E, vector fields in E, or a vector field in V, taking dual 6 plane field, integrating it, getting to 2 kind of Calabi-Yau manifolds, and then checking duality conditions on them. Like we wrote a subsequent paper applying this to Joyce manifold, for instance. I think your approach is similar, somewhat similar, but you have this instanton. We really didn't look at the instantons. We more like topologically, we were trying to understand some kind of duality. So, I mean, are your papers in archives? Maybe I can look at them and see, study them and see the relation, what we were doing.
Okay, so you assume the existence of two plane fields and consider the splitting of the tangent bundle E plus B.
Yeah, starting point, yes.
Yeah. So it's like so yeah, I'm checking your paper very rapidly. So
yeah, I mean, this is just I don't know. I didn't mean to disturb your talk, but I think it is good to talk to each other. You know, I didn't know about your work.
Yes.
I can look at your paper and see if there are some relations to this.
Yes. So yeah, our paper is originated from the paper by and D and Liang. So, this paper. So
yes.
So we followed the setting of these guys. So I'm not sure it is related to your works.
So Kotaro, that means that because of the real Fourier Mukai transformation, that means that the deformed Donaldson-Thomas cognition are more natural than undeformed, right? You don't have so that's actually I want to ask you that in some senses that study Donaldson-Thomas cognition is more natural than study Donaldson. We have such kind of the transformation, right? What is the better to study Donaldson-Thomas cognition or deformed Donaldson-Thomas cognition? What for you? What is the more natural to study, or at least easier analytically? Whatever. What do you prefer to study?
Sorry,
Undeformed or deformed?
Because of the internet connection, I cannot hear you well. So
same here.
I see.
I don't hear Hong Wan Lee clearly, but I do hear Kotaro clearly. I think something. Something with your name.
I already. Okay. Yes. Happen.
Oh, sorry. I can't hear you.
Okay, so I should ask later.
Okay.
Okay, thank you very much.
Yeah.
Yeah.
Yes, very good. Yeah.
Yeah, thank you. Thank you for interest.
So I'm sorry, that's internet the provider. I mean that I already have the controls, but I cannot control all the time. Yes, so I only done so you don't hear me. So
okay, so since Fan has some internet connection problems, let me just ask if there are any remaining questions. No, if not, then let's thank Kotaro again for a very nice talk.
Thank you.